Okay. So welcome to this lecture of the 19th of December, 2016. And today we will continue our lecture on the topic of exponentials and logarithms. Okay, so let me first check to see that this is coming on live okay. We're on the topic of exponentials and logarithms. So I'll mute that and we'll continue with this lecture. Okay, so last time, if you'll recall, we were looking at the definition of logarithm as the inverse function of the exponential function. And so we would be able to evaluate, so I was showing you various valuations of that function with a given base and with the argument and the final result. Okay. So recall that if you have the base b, then the logarithm function is defined as f of x is equal to the log base b of x. We can call that y. And so this the values of x and y that will occur here will be such that if you operate on y by the exponential function, then you get back x. So this is these two are equivalent. This is the it's called the exponential version of the logarithmic equation. The exponential version, or the expression of the logarithmic equation or version. So they're basically the same thing. And so if you are wanting to interpret this equation properly and you understand this a bit better, then by all means transfer this into this form first, and then this will allow you to finish an evaluation or solve an equation or whatever, or graph even. Okay. So I want to do a bit more on, and one other thing, the b again is always positive. It's never 1, so b is either a real number between 0 and 1, or b is greater than 1. And also x, let's just consider the domain and range. Okay, for the exponential function, the domain is so if we have y is equal to b to the x, so putting it in that usual form where x is the input, y is the output, for the exponential function, the domain of the exponential function is all real numbers, right? So you can put any real number in for x and you'll get a value for y. But the range, so remember what it looks like graphically, it's always, if you have a just a simple exponential function like that, then the graph is either going up like this or going down like this. In both cases, it is the y values are always positive. And if you stick a factor in front, then depending on whether a is positive or negative, the range will be okay. Something happened. Oh, hello. Okay, somebody's chatting here. Okay, so if you can chat possibly on the live stream, that would be nice. In any case, if you want to use Skype, that's fine as well. I'll check the chat here. Okay, so going back to this range, the range will be the same as here if A is positive, so that does not change the range, just scales it in the y direction. But this value of A in front will make the range negative. So it just means you flip the graph over the y-axis like this. Okay, so that's for the exponential function. Now for the logarithm function, you would have the domain and range switching, because that's what happens for an inverse function. This is the inverse function of this one, and so the domain is, for this simple logarithm function, it's going to be all the real numbers, all the positive real numbers, so not including 0. Right? And the range will be all real numbers, or from minus infinity to plus infinity. Okay, so that's the comparison of the two cases. The graphs will, for these functions, will look like the same as the graphs over here, except they are flipped across the x equals y line, y equals x line. Okay, so that will give you graphs like this. So you'll have, for the typical logarithms, for a base b which is bigger than 1, you'll have this kind of graph. This will be the point 1, 0. And for graphs like this, where b is less than 1, you'll have it going the other way, downward like this. Let's just erase this. It's a bit way. Okay. Okay, so this would be y equals log base b of x for b greater than 1. And this will be y is equal to, so the same function, but b less than 1. Okay. So, yeah, so any questions? If you have any questions, just try asking on the chat. Okay. So, now let's do a few more try-it problems from the textbook. All right, so shifting exponential functions. Let's see some problems there. So try it number 6 is a section I believe 6.2, and it's try it number 6. All right, so f of x, you start with a basic exponential function, e to the power x. So the base is e. And you're told this is compressed vertically by a factor of 1/3. have to watch the order in which these operations are done, because that matters. Reflected across the x-axis. And then shifted down 2 units. Okay, so write the expression down for the new function. Okay, let's call the new one g. So we should be able to write this all down now in one step. So first, the function is compressed vertically by a factor of 1/3. So that means we multiply the function by, on the outside, right, in front, by 1/3. Then it is reflected across the x-axis. So that would mean a reflection in the about the x-axis, okay, would mean a flip, so from positive y to negative y. So that means the negative sign out in front of the function again. And then it's shifted down 2 units. So that means everything is shifted down. You subtract 2 from y. Okay. And so it comes on the outside of the function again. So nothing is done directly to the x here, either shifting or changing by a minus sign, putting a minus sign in there, which would be a reflection about the y-axis. Okay, so that's what I would expect to get. All right. And what would the graph look like? Okay, let's see what the graph would look like. It's always helpful to visualize this. Okay, so it's the graph of e to the x, which looks something like this. Here's 1, 2, and at x equals 1, we get the value e, which is about 2.7, is about up here. This is 2, this is 3, this is 1, the graph goes through 1, and at minus 1, it's roughly 1/3, so it's down here, somewhere here. So the graph looks something like this. And then you compress by a factor of 1/3 vertically, so that will shift it. So that will make this value even smaller, and we'll get it over like this. And then this will be less than 1 here, because that's less than 1. That's less than 3. So that's 1/3 e to the x. And then we reflect it across the x-axis. So here's the x-axis. And so all these values get mapped here. So right, you can think of it, each individual value gets mapped to a corresponding one over here. The y value gets mapped to minus y, y minus y to minus y, but the x's stay the same. So that's what it looks like, something like that. And of course, the graph continues on in both directions. And then the final one is subtract 2, so all the values of y get 2 subtracted from them. So shifted down 2 units. So we have to 1, 2. So somewhere down here is where it goes. And now it's important to bring along also the asymptote, because it's a major feature of this graph. So the asymptote also gets shifted down by 2 units. Okay, so here's the asymptote, horizontal asymptote. And it's already kind of difficult to draw because it's off the page, but this will go down. Again, this is less than minus 1. So it's somewhat off the page here, but if I had more room, I would shift it back here like that. Well, let's just draw it again. Yeah, so the final version will be that shifted part there. Minus 1, minus 2. Here is minus 2. Here's the asymptote. Y equals minus 2. and here's the graph -1. Okay, -1 is here, +1 is here. And it's, as I said, very small value here. This is about 1/3 of the way between them two, and this is just about as went up to 1. Okay, so just based on about 3 points, that's what I can do. Now in Maple TA, by the way, you'll be able to, I'll give you some problems where you'll be asked to graph a given logarithm function. And it'll give you a tool where you choose the asymptote, the horizontal asymptote, and then you choose 2 points on the graph. And actually those 3 things will determine the whole graph, the whole behavior of the graph. Okay, so yeah, and that's similar to some of the other functions. For a straight line, it's easy. You just find 2 points, and then that gives you the straight line. So this in the sketching, these are in sketching questions. So you learned how to do that, I hope, already. For another function, for the parabola, for the quadratic functions, you choose 1 point and it will give you the vertex. You choose the other point and it will give you the rest of the parabola. And so you only need those 2 points. The vertex is actually two parameters, and the third point gives you specifies a third parameter. There's 3 parameters in any quadratic: a, b, and c. In this formula, ax squared plus bx plus c. Whereas this has only 2 parameters. So specifying 2 points in the line specifies the whole line. Specifying the vertex and another point of the parabola gives you the whole parabola. And for a logarithm function, I guess you have to specify the base as well. Yeah, you have to specify the base and the asymptote. And then you would give two points, and that would give you the complete graph. So that draws you any exponential function on the one hand, and then also that will also work for any logarithm function. You can also do that for any logarithm function. All right. So I'll give you some practice with that by giving you some Maple TA problems. All right. Okay, so another problem. Let's go on to, yeah, so I'm not going to do all of the tried problems for section 6.2. So I'll just ask you to go through try them yourself. Do the remaining ones I haven't done, please. And I will start with the next section well, I'll continue in the next section. We've already started the next section. So section 6.3 had to do with now the logarithm function. I will continue to do problems in that. So there were several triad problems I wanted to go through. Triad number 2. Actually, first, let's do triad number 1. So they ask you to write an exponential form. Okay, so this thing, okay, I might have written this down before as an example where you have to evaluate it. But this tells you 1 million is raised to the power, okay, what power of 10 gives you 1 million? The answer is 6. So the corresponding exponential form is you put down a base on this side, you put the 6 over here, and then the million goes on the other side. Okay. So 1 million has 6 zeros and a 1. These commas are just placement markers, just indicate every 3 zeros. So it helps you to more quickly read off the number. Okay, another one is log base 5 of 25 is equal to 2. And that means that 5 must be raised to what power to get 25? And the answer is 2. So I can just write that down. And that's equivalent. Okay, so these are the answers for the exponential form. Exponential version, I called it, but exponential form. Yeah, I should write those as logarithmic form and the exponential form. Okay. All right. Now the next one, try it number 2. This is again section 6.3. Is write in logarithmic form. Given the exponential form, so that's we're given 3 squared is 9. Okay, so to write it in exponential form, we write it as a question, 3 raised to what power gives you 9? So if the base then is 3, the number that you are putting in as an argument is 9, and you're asking what power do I have to raise 3 to get 9, and the answer is 2. Okay, so that's the corresponding logarithmic form. Now, so if you have 5 cubed is 125. Okay, so log base 5 again is the base of 125 is 3. Okay, so notice in these cases, if I have the function with the base on this side, if I keep the base on this side, somewhere within the function, so the bases are 5, 3, 3, 5, and 5, then whatever values I have here and here get switched, or sorry, here and here, the 2 in the exponent and the 9 on the other side, those get switched. Likewise here, the 3 and the 125 get switched from one side to the other. Okay, so if I keep the base on one side, then to go from logarithmic to exponential form, I have to switch the x and the y. The positions go from one side of the equation to the other. Okay, of course I have to put them in their proper places within the function. All right, and finally 2 to the minus 1 is 1/2. Exponential form is log base 2 of final value 1/2 is minus 1. Okay. All right. Yeah, feel free if you have questions to just send them in through chat. I'll periodically check the chat here. see if you've asked a question. We're talking about the chat in the YouTube channel. If you're watching this live. All right. So if you're not watching it live, then that chat will not work, so please do send it in some other way or by email. Thank you. All right, so evaluate an example that I show a similar example in the text, but how would you evaluate this? So it's log base 5 over 4 of 25 over 16. Okay, so if you're asked to evaluate and you don't know it's not easy to tell the answer, then a tool or a helpful thing to do is just go to the exponential form, and then let's see if that makes it any simpler. So switch the x and the y. This is the x, that's the y. And so you get, the base is 5 over 4, so I write this in exponential form. So 5 over the 4 to the y is equal to 25 over 16. What is y? And the answer is easy to see now. This is, if I square 5, I get 25. If I square 4, I get 16. So a square over here does it. Gives me the correct answer, or the correct equation. So y is equal to 2. So that's my evaluation, y equals 2. All right. Some of these you'll need to use a calculator. So if you don't already have a calculator, it doesn't have to be a graphing calculator, but any small, calculators are about $10 now or something. Hopefully not too expensive, but anyway, you'll have the ln. Most of them will have ln, which is the natural logarithm function, and they'll just have a log function as well, any of them. And later on we'll see how to convert from one logarithm with one base to another logarithm with a different base. So you can perform any logarithm function on a calculator based on with any base that you like. Okay, so ln of x. Let's say you want to evaluate ln the natural logarithm of 500. So this is, you're going to answer the question, what power do I have to raise e to get 500? So remember, e is some irrational number, and it's somewhere 2.718, etc. So it's some irrational number, and it's not easy to see what power I have to raise that to get 500. So a calculator is pretty much indispensable now to find logarithms. Used to have to use tables, but then calculators came along, and now people don't need tables anymore. So using a calculator, you just plug it into the natural log function, and you get this number 6.2146, and so on. If you try, this is another try question, try at 8. That was an example. So try at 8. If you put in ln minus 500 into the calculator, what do you suppose you'll get? Okay, well, we'll just say error. Right, so the negative sign means that, there's no number when raised to the power, when you take e raised to what power gives you minus 500, the answer is no number will do that, because whenever you take e raised to some power, you always get a positive number, and this is negative. So this is in other words, this is out of the domain of the natural logarithm. Minus 500 is not in the domain. domain of this function ln x. All right. Okay, so let's try looking at some graphs or domain and range questions here. Okay, so this is triad number, this is now in section 6.4. Triad number 1. What is the domain of f of x is equal to log base 5 of x minus 2 plus 1. Also, my question is what is the range? Okay, so here we have a logarithm function with base, that should say 5. Base 5 of, in brackets, x minus 2 plus 1. So we can start with a simple logarithm function, log base 5. And what do we do to get this function? We have to shift x, or shift in the horizontal direction by 2. Because we're subtracting here, that will be shifting this function to the right by 2. And then when we're adding 1, that means we shift the whole graph of this thing up by 1. So it will look something like, when we plot it, it will look like point where it goes through on the x-axis is at 1 for the simple logarithm function. So if I shift it over 2, that point will be over here. And the next value will give me y equals 5, so it will be way up here. That would be already all the way up here somewhere. And at x equals, that's at 3. And then at x equals 1, it's all the way down to 1 over 5. Okay, so it's going to increase pretty quickly here. And it's shifted down by, it's shifted up by 1, so then we have to shift everything up by 1 like this. And the asymptote will be, the new asymptote will be y equals 1. So the final answer will be this second graph that I've drawn here. The domain, then, is, oh, I'm sorry, I drew the exponential function, didn't I? Sorry. Okay, let's erase that. Okay, so the logarithm function is I have to flip the simple exponential function first over the x equals y line. All right, so let's see how that looks like. So this point 1, 0, or 0, 1 will be mapped into 1, 0 by that flip. So go through here. Also at x equals 1, okay, if I look at 5 to the power x, that's my original exponential function. Again, it will go through 1 at x equals 0, minus 1 will go through 1 over 5, and at plus 1 it will go through 5. Let me just draw the graph up there. 1, 2, 3, 4, 5. Okay, so drawing it like that. So this point will get mapped to, I have to go all the way up to 4, 5 here. So 1, 5 gets mapped to 5, 1. So this will look like this. So this point is 0, 1, and it gets mapped to 1, 0. So you just flip the x and the y around, right? And that gives you the point on the inverse graph, the graph of the inverse function. And this point here was minus 1 and 1 over 5. It gets mapped to 1 over 5 minus 1. Okay, so this is my basic function now. Y is equal to the log base 5 of x. And now I want to shift it by 2 in the x direction. So that means I just shift this point over here. And then the asymptote now, the asymptote is y equals, or x equals 0. It's a vertical asymptote for the logarithm function. So for the exponential function, I had a horizontal asymptote, y equals 0. Y equals 5 to the power x, that has an asymptote of y equals 0. The x equals 0 is a vertical asymptote for the logarithm function y equals log base 5 of x. All right, so that gets shifted along with everything else, all the x values. The y values stay the same, but the x values all shift by 2 when I do this operation. And then when I add 1, I shift all the y values, keeping the x values the same, up by 1. All right, so the graph will look then like, let's see if I can put it in the final form. 1, 2, 3, goes through 3, and then I have to shift it up 1. So it goes through this point. There is a vertical asymptote at now x equals 2. And the value at 1, 5, minus 1 gets shifted up by 1 and then across by 2. So that will be now through the x-axis there. It's 1, just 2 plus 1 over 5. So that will be 2 and a fifth, 0. That will go through the graph, or the x-axis. That would be a point on the graph going through the x-axis. So it's an x-intercept. And then at this point gets shifted up by 1 and across by 2. So this will be all the way over at 7. 1, 2, 3, 4, 5, 6, 7. And it will be up at 2. It will be the point 7, 2. And if I graph all the points, it will look something like this. This is a point 3, 1. Okay, 3, 4, 6, and 7. All right. Okay, so again, that will be the answer to this triad question. Oh, and the domain, actually the domain is what we really wanted here. we didn't have to sketch this, but just so you see what it looks like. Once you see what it looks like, that really helps to find the domain. And see, the domain is then all real numbers between 2 and infinity, not including 2. Okay, so if I can't choose 2 directly, that would give me a negatively infinite value. So I have to choose anything greater than 2, strictly greater than 2. So 2 is not included in the endpoint of this interval. Okay, so anything bigger than 2 will also work in the logarithm function. Anything less than 2, or 2 or less, doesn't work. It will give you an undefined value. Okay, so, and the +1 doesn't really matter here. The base doesn't really matter. So actually, you could read off the answer right in the beginning. You just need x minus 2 is greater than 0, and that immediately gives x is in this domain. Okay, I'm just drawing the graph is helpful for seeing what else is going on in the graph, and just to show you, there's nothing really significant about. You could change the 5 or you could change the 1, and that does not change the domain because you're not shifting in this direction. The shift does matter in this direction. It does change the domain when you shift there, but not in this direction. And the range, by the way. The range is, again, it doesn't depend on the horizontal shift. It doesn't actually depend on either the horizontal or the vertical shift now. Because when I shift the graph up or down, the range is still minus infinity to plus infinity. Okay, the y values will range all the way from minus infinity to plus infinity. Okay, and that doesn't depend on the base as long as the base is not equal to 1. Which we restrict ourselves away from. All right. Another similar problem is find what is the domain of log of x minus 5 plus 2. Okay, so let's try number 2. All right, so again, the 2 and the base don't matter. This actually means log base 10, by the way. That's what it's usually taken to mean, according to convention. And the only thing that matters here is the shift in the positive x direction, to the right in the horizontal direction. And so that means that the range is wherever x minus 5 is greater than 0. Those are the defined values for the logarithm function here. And that means x is greater than 5. So the domain is 5 infinity. Okay. So we can just write that down. And the graph will look something, well, it'll be above 5. It'll have an asymptote of x equals 5. It will have a range again of all reals, but it will have a different shape and a different shift in the x direction, or in the y direction as well. So that will not change the range or the domain. Try number 3. Graph f of x is equal to graph f of x is equal to log base 1 over 5 of x. State the domain, range, and asymptote. Domain, range, and asymptote. right. Okay, so now here we have a base which is less than 1 over 5. All right, so recall what the graphs should look like. They will be, again, be a vertical asymptote. The vertical asymptote here, by the way, is at x equals 0. So that will be down the y-axis like this. So we can say that right away. And the graph will, instead of going up like this, it will go down like this. It will pass through the point 1, 0, because if you plug in 1, right, the thing that you have to raise 1 over 5 to get 1 is always 0. So the y value will be 0. So that's a point in the graph. It'll go down like this because at x equals 1, you can draw a table too. That will always help to help us to understand and describe the graph. X equals, as I say, 1 gives you y equals 0. If you go to x equals 5, let's say, so up along here, 1, 2, 3, 4, 5, what should we get? What do I have to raise 1 over 5 to get 5? The answer is minus 1. So I get negative 1 here for y. And going the other way, 1 over 5, what power do I have to raise 1 over 5 to get 1 over 5? And the answer is just 1. So I have to go to 1 over 5. The 1 over 5 is right about here. Then I get 1. So you can see the graph will be coming down. As x goes to 0, from positive values, I will get, y will go to plus infinity. And as x goes to plus infinity, y will also go to plus infinity. Okay, so here as x goes to 0 from above, y goes to plus infinity. Sorry, y will go to minus infinity here. All right. If I had base 5 here, then the graph will look like what? It will just be this graph flipped about the x-axis. So these values here will go down here, and this value will go up here. This value will stay the same. So this is a function y is equal to log base 5 of x, which I showed before. And it should just be symmetric to this graph. It's not quite, because this axis is not quite straight, so let's draw it straighter. All right, and right, the asymptote is the same. There's only the vertical asymptote. There's no horizontal asymptote because both these go off to infinity in x and y. As x goes to infinity for this function, y goes to plus infinity. Okay, I'll emphasize that with a plus here. And as x goes to 0 from the right, y goes to minus infinity. Okay, so that's graphing this function. So I've graphed the correct function here. Use a different color for the change here. so that's my answer like that, something like that. This part gets closer and closer to the positive y-axis. As x goes to 0, y goes to plus infinity. And the domain is all positive real numbers. Zero to infinity, not including 0. The range is all real numbers. And the asymptote is given here. All right. So that answers all those questions about the graph of this function. Number 4. And you usually call the graph of, we have a starting graph, and then we'll call that starting graph the parent function. Like here I have the parent function log base 5 of x, and when I flipped it, then I would get the function y is equal to log base 1 over 5 of x. Okay. Why do you get the flip just by replacing y by 1 over 5 by 1 over 5? Okay, so let's see, if I look at the exponential form, okay, so my original parent function, let's call it f of x, is equal to log base 5 of x. This is my parent function. And then I will call g of x. G of x is log base 1 over 5 of x. Child function, or I guess it's the child of the parent. It came from the parent. So let's okay. So how do you show that this function is simply it's going to actually be the negative of this function? So it's just this function flipped over the x-axis. So it means all the values of y have changed by multiplying by a minus sign. If they're positive, then they become negative. If they're 0, it stays the same. If it's negative, then it becomes positive. Actually, yeah. Negative becomes positive, positive becomes negative. Okay, so why is that true? All right, so here we need to use the definition of we want to prove this. Let's try to prove this. So we're not sure at first, perhaps, that it is true. So we put a question mark here for the inequality. So this is true if I can write so I write both sides as y. I write this side as y. And this side is z, let's say. And I want to show that y equals z in the end. So if I write this as y, that's equivalent to the exponential form, which is 1 over 5 to the power y is equal to x, right? I have the same value of x over here, so I rewrite this also in exponential form. And I put the minus sign over there first. And then it becomes 5 raised to that power is equal to x. So these are the exponential forms of this equation and this equation. Now, is this true? If let's see, when is this true? So x is equal to this x, so that would mean that 1 over 5 to the power y is equal to 5 to the power minus z. But I can replace this whole thing by 1 over 5 because the negative sign means take the reciprocal first. I have a negative sign in the exponent. So then the y, 1 over 5 raised to the power y is equal to 1 over 5 raised to the power z. Or I could also do it by rewriting this as 5 to the minus y. And in the end, I'll get the same thing. So this equation, for this to equal this, the only way I can have that be true is if y is equal to z. Because, although I didn't state it before explicitly, this function, the exponential function, is always a one-to-one function. The exponential function, b to the x, as long as b is not equal to 1, is a one-to-one function over its entire domain, which is the real numbers. Okay, so if it's one-to-one, it means that the looks like this. So if I have one value of y equal to another value of y, the only way that can happen is if the values of x are the same. The arguments of the exponential function are the same. So this can only be true if y is equal to z. And that's what I wanted to prove. Okay, so here I've shown why it's true that in order to transfer from a base to 1 over that same base, in order to describe the new logarithm function with respect to the new base, where you have the same argument x in both cases, all you have to do is change the y values by multiplying by minus 1. In other words, flipping the graph over the x-axis. Okay, so that's why that is. These graphs are reflections of each other. So we're going to try it number 3. Chart number 3 says oh, I did that already. I just did that. Okay, so chart number 4 says sketch a graph of log base 3 of x plus 4 alongside its parent function. And include any key points and asymptotes on the graph. So the key points would be points like what I had before, the value of, in the parent function you'll have the value 1, 0. Okay, and then you also have the b, log base b of x is the function, is its parent function. That's going to be the parent function. And so 1, 0 is always on the graph. And b1 is always on the graph. And maybe another key point would be 1 over b minus 1 is always on the graph. Okay, so those would be key points. on the graph. And the asymptote would be x equals 0. Let's draw the asymptote in blue. Okay, so this function now, the base is 3, and it's shifted to the left by 4 because I'm adding 4 to x. Okay, so what that then looks like is 1, 2, 3, 4. Let's draw it like that. And base 3, so that's going to be our new asymptote. At x equals -4. The key points, one of the key points will be, in the original graph, will be 1, 0, and that will get shifted to, from here, 4 over to the left. So I have to subtract 4 from 1, and that way I get -3. So the answer, the y value stays the same, so it's still 0. So I get the key point -3, 0. That's one key point. Another key point will be 3, 1. The base b is b equals 3. So the point 3, 1 will get shifted by 4 again to the left, so that I subtract 4 just from the 3, and I get -1. 3 minus 4 is -1, so it's up here at 1. I don't have any shifts in the horizontal direction anymore. So that's another key point. And finally, a third key point would be, that's -1 and 1. The third key point would be this one, which is 1 over 3 minus 4 minus 1, which is -12 over 3 is -11 over 3 minus 1. It's very close to -4. It's about right here. Okay, so those are 3 key points, and the asymptote. And this goes above, not through 1 on the x-axis, but above it. Okay, so that's a sketch of this graph, log base 3 of x plus 4 alongside its parent function. Okay, well, I didn't draw that in. The parent function should be also in here. So it goes through 1, 0, 1, 2, 3, 1, and 1/3 -1. Okay, so it looks something like that. Okay, please note one thing. These graphs look like they're very flat here, but there's no asymptote, there's no horizontal asymptote. There's only this vertical asymptote here, and the parent function has a vertical asymptote here. Okay, so these graphs, although they look flat here, I'm just trying to show that it increases to infinity, but very slowly. All right, this graph as well. It should just be the shift of this is the same as a parent graph, except shifted over by -4 in the x direction. All right, so that's the graph of that they're asking for there. Include the key points and the asymptotes in the graph. Find the domain, range, and asymptote. All right, the domain and range are, domain is from -4 to infinity. The range is all reals. So from -infinity to +infinity. And the asymptote is x equals -4. Okay, so that answers the question. A similar question is f of x is log base 2 of x plus 2. The log base, we'll just say, log base 2 of x plus 2. So again, I think the instructions are, this is number 5, sketch the graph alongside its parent function and include key points and asymptotes on the graph. So the parent function has this, goes through 1, 0, and then 2, 1, and 1/2 -1. Those are key points. Okay, it goes to infinity a little bit faster, but still it's not very fast. So that's the parent function of this graph, and then you shift it up by 2 in the vertical direction by adding 2 there. So then this key point goes over to this one, which is 2, 0. This one goes over to, just add 2 to the y. I'm sorry, just add 2 to the y, and it should be 1, 2. This should go up to 2, 3. And this point over here goes up to 1/2 plus 1. And the asymptote is still the x equals 0. So those will be 3 key points, and that's going to be the shape of the graph. It's the original parent graph shifted up by 2. And so the domain is real numbers from 0 to infinity. The range is all real numbers. And the asymptote is the vertical asymptote, x equals 0. So the shifting in the y direction does not change the vertical asymptote. Number 6, f of x is 1/2 log base 4 of x. Okay. Let's see what the parent function looks like in log base 4. Looks like this. You have 1, 2, 3, 4 Key points are 1, 0, 4, 1, and 1/4, 1/4, -1. So the graph, the parent graph looks like this. All right, and something like that. And then you multiply by 1/2. So that will shrink everything in the y direction by a factor of 1/2. So this point will stay the same. This point will go to 4 1/2. And this point will go to 1/4 minus 1/2. So let's draw it as a red line. This is a graph here. Now, I want to show you, I don't think they did it in the book, but this could also be written using some algebra, using our rules for logarithms and exponentials. This f of x can be written as log base 16 of x. Okay, so why is that true? So in other words, when you stretch or shrink in the y direction, you do that to a basic logarithm function with a certain base. Then what the effect of that is to replace the base by another base. Okay, and so we'll see this obeys a rule that we'll see later for changing the base of a logarithm. All right, and okay, let's just see how that works. So this I'll call y is 1/2 log base 4, and then what I want to show that is that's equal to z, which is log base 16 of x. Can I show these are the same? That y equals x. Okay, so let's convert this to exponential form, and then I have to put the 2 over with the y here. So let's solve for x in terms of y. 2y is equal to log base 4 of x, and then I replace this by the exponential form, which is x is equal to 4 to the 2y. So it's 2 times y there. Meanwhile, I replace this. I just have to replace it by the exponential form. It's already in its most simple form. So x is equal to 16 to the power z. But here now I can express this using the rules for exponentials. This power here is 2 times y. So I can express it as first taking 4 squared and then to the power y. So the 4 squared there gives me 16 to the power y. And now this x should be equal to this x. So 16 to the power y is equal to 16 to the power z. And remember, any exponential function with any base that we're allowed to use is a one-to-one function. So this means that y is equal to z. So that's what I wanted to prove. Okay, so this indeed is true. Okay, so this is a general way that you can use to show that when you scale by a factor in the y direction any basic logarithm function, you get another basic logarithm function with a different base. All right. And you can check the values individually too. If you plug in 4 here, 16 raised to what power gives you 4? You know, you're going to see, well, you have to take the square root of 16, which is a power of 1/2, and that's the correct answer there. All right? Same point for this, 1 raised to what, or sorry, yeah, 1 raised to what power of 16 raised to what power gives you gives you 1, and the answer is 0, so that's fine. Same as what you get over here. And this one is 1/4 raised to what power of, oh, I forgot to write it in this point here. 1/4, and this is minus 1/2. So 16 raised to what power gives you minus 1/2? Sorry, gives you 1/4. That's the answer, and this is going to be the, yeah, the question is what is the value you have to raise 16 to? 16 to the power what gives you plus 1/4. And there you can see the answer will be, you take the square root and then you take minus the square root, so you get 1/4. Or 1/2. 1/2 is the correct exponent that you have to put in here. And that will take the square root of 16 and then invert it, take the reciprocal, giving the final result of 1/4. Okay, so that answers the question. To what power do you have to raise 16 to get 1/4? All right, so those 3 values are like a check for that answer there. Okay, you might check some things out here. Log 4 of x times 2. Okay, you might want to at home try to verify, is this equal to, what is this equal to? What other base is this equal to? All right. Well, let's if you want to try it, you can, and you're not watching this live and you just want to try it yourself, you can just press pause and then try it. So okay, so let me do the problem now, and it's going to be so I'll call this x, or sorry, I call this y, and the other part z. Okay, I'll start with these two. And then I change into exponential form, and I get y/2 is equal to log base 4 of x. And then I change it again. Exponential form gives me y/2 to the, so 4 to the y/2 gives me x. Here it is b to the z gives me x. And here I can take the 1/2 in with the fourth, and then raise it to the power y. That gives me x. And 4 to the 1/2 is just the square root of 4, which is 2. So 2 to the y equals x. And if x equals, or y equals z, okay, so I'm saying this is equal to this, find b. So the y must be equal to z, and therefore the b to the y must be x. So that's only true when the bases are the same. So b is equal to 2. Okay. So I trust you're following this, and if not, then please let me know as soon as possible by asking a question and trying to clarify for yourself. There's also the textbook to read that. There's also Mr. Maksudi, my son, who is available as a tutor. So either G2, please contact him or me or somebody about that as soon as possible if you have any problems understanding this material. All right, let's go on, see if there's anything more that I wanted to do here. Well, yes, there are a few more problems. So find the sketch of these graphs. These are try it 7, 8, 9, and 10. In the section, possibly the next section actually, 6.4. I think I did 6.4 right now, yeah. So try number 7 says sketch the graph of f of x is equal to 3 log base x minus 2. The base is not given, so we know that the base is actually 10. State the domain. Range. And the asymptote. All right. So let's see what this looks like. Log base 10 means we have 3 key points starting from the parent function of 1, 0, and then 10, 1, and then 1 over 10 minus 1. These get shifted over by this to, I multiply y only by 3, and I subtract, from each value of x I subtract 2. Sorry, I add 2 to get a new value. So the shift is to the right, so I have to add values to the value 2 to x. So 3, I multiply this by 3 and add 1 to get the new y value. So I get just 1 there. And this one I add 2, so I get 12. Multiply by 3 is 3, and add 1 is 4. And this one I add 2 to this, so I get 2.1. This is 0.1. So adding 2 gives me 2.1. And then minus 1 times 3 is minus 3, plus 1 is minus 2. The asymptote is at x equals 2. The domain will be given by x greater than 2, so the domain is all values from 2 to infinity. And the range is all reals. Asymptote x equals 2. So the key points are 1, 0 gets shifted to 3, 1, so that's going to be here. Here's 1. Okay. And then 12, 4, so it's going to be way up here, 12, and then 4. If I want to scrunch everything in, maybe that's the better thing to do here. So here's 1. Let's say 1, 2, 3, 4, 5. This is actually starting at, oh, okay. I have to shift things around here, sorry. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's my vertical asymptote, x equals 2. Here's my y-axis. And then 3, 1 is up here somewhere. 3, 1 is here. And then 12, 2 is This is in the way now, so I'll just write it up here. And then 2.1 minus 2 is right here. Sorry, that should be at 4. So 1, 2, 3, 4. So that should be right up in here. That's 3, 1, and this is 2.1 minus 2. So hence the graph looks something like this. Okay. All right, so the stretch in the y direction, there's a stretch in the y direction of a factor 3, and that means that instead of this getting shifted to, this gets shifted by 1. There's no stretch happens if the point starts in the y, on the x-axis. But the next point will be at 10, 1. So it started over here, 10, 1. And then you stretch it up to 3, 1, or 10, 3. And then you shift everything up by, you shift everything up by 1 and over by 2. So that gives you this final value of 12, 4. Okay. And this value 1 over 10, this was 1 over 10 minus 1. Oh, sorry, I think I might need to do something here. Yeah, multiply this by 3 first, and then shift it up by 1. Oh no, I'm fine. I just have to shift it over to the right by 2, so I get 2.1, that's fine. And then the y value gets multiplied by 3, you get minus 3, and add 1, it's minus 2. So that is correct there. So the key points all get simply shifted in the x direction, and in the y direction they get first stretched away from each other. The differences will then be, instead of being 1 different in the y direction, there's 3 different in the y direction. This is 3, 1, now this is 12, 4. So the y values are 1 and 4. And then this is minus 2 and 1. So the difference between them are now 3. The differences between them are 3 in the y direction. But there's no stretching in the x direction, just a shift. And in the y direction there's also a shift, but that does not change the fact that the y values are different by 3. Okay, so that's number 8. Number 7. Number 8 is sketch the graph of f of x is equal to f of x is equal to minus log of minus x. So again, this is log base 10. And I have a negative sign in front of the x, so I start with the parent function, which has key values at 1, 0, 10, 1. It's way over here. 1 over 10, 1. 1 over 10 minus 1. And then when I change by a minus sign there, that flips the graph about the y-axis. So that will change it over to this. And when I change the overall minus if I put an overall minus sign in front of it like that, that changes the y values also by -1. So this whole thing will get transformed into this. Now this key point will get mapped up to here. So it's just an odd reflection now, a reflection about the origin. I changed the signs of both x and y. So it will come down like this now. And -10 will be way over here somewhere. -10 -1 will be right here. And this will be -1/10 plus 1. And this will be -1, 0. All right, so the graph will look like this. The y-axis will be the asymptote. Oh, at least from the other graph. It should be x, so the asymptote will be x equals 0. The domain will be all the negative real numbers, so -infinity to 0, and the range will be all real numbers, because again I'll go from -infinity to +infinity. So I'm answering the same question as I did for number 7. I sketched the graph, I stated the domain, the range, and the asymptote. Number 9 I'll skip. It's a graphical question. And number 10, what's the vertical asymptote of f of x is equal to 3 plus natural logarithm of x minus 1? Read that out again. Number 10, try it number 10. What's the vertical, oops. Vertical asymptote of f of x is equal to 3 plus ln of x minus 1. All right, so, okay, so based on all these examples, if you think about it, all you need to do is look at the argument of the logarithm function. The value of x which makes the argument of the logarithm function 0 is what also gives you the vertical asymptote. Okay, the shift here in the y direction does not change that vertical asymptote. So we saw it over here. If we take the argument to be 0 for the logarithm, even though that's undefined for the logarithm, we would still ask the question, what is the value of x for which that argument is 0? Or what is the value of minus x? And the answer is x equals 0. So that just gives us the asymptote in that example, for example. And that will work for all the examples that we've seen so far. So you just equate the argument to 0 in the logarithm function, and then that gives you the answer. So that will work for any base as well. Okay, so with that, I've kind of completed the coverage I wanted to do for this section. And the next section will deal with operations rules involving logarithms and exponentials. And so I think we're already gone enough into this, so it's a little bit overtime right now. So I'll stop the lecture there. We'll just say Hudofis, have a good day. Take care, and see you next time, which hopefully will be on Thursday. And I'll give you a problem set too, so I can do a quiz on Monday, if I could. All right, so have a good day, Hudofis, and Shabakush. Good night.